What's happening? Well, currently I am trying to figure out how to find the comments on my iPad. Man, I would have never guessed the person with the Hayward last name was Miles. Hi, Seth. I am just interrupting my relaxing Sunday night with some live streaming calculus. And it's 7 o'clock, and there are 19 people here, so I think it's time to get rolling. And gosh darn it, I cannot figure out how to make my iPad show what I want it to show. Oh, what? It's so weird. Okay, no, never mind. I can kind of see it. Alright. Yeah, Ryan, I'm not an OBS. It's not infinite. Alright. So I guess I'd start with the quizzes, which I have not put in the gradebook, so I don't know what the averages are, but I know people did really crappy in the first section from grading it, comparatively to the others. Oops, that's not what I wanted. Alright, so in this first question, a lot of people got tripped up by this. We had one example like this in our notes, but it was... some people, I guess, lost it in translation. The big idea here is that we're supposed to separate this addition in the integral into two different integrals, which we handle separately. So first I have the integral from a to b of f of x dx, and then I have the integral from a to b of 2x dx. And the nice part is, I know what the integral from a to b of f of x dx is. It's a plus 2b. So I just replace that with a plus 2b. And then this integral, the a to b of 2x dx, I need to actually integrate. So I integrate it, and I get x squared. And then I just plug in my bounds, and I get a plus 2b plus b squared minus a squared. And this was the answer for like half of the folks. The other one, I think you were integrating like 3 or something. And it was similar. You had to split it up into 2 separate integrals and then handle each of them separately. Now most people didn't do this, so there are a lot. It was kind of a bloody area for people. Now, the other problem was also pretty get wrecked for people because you had to plug in x squared for y in both places, and then a bunch of people wanted to do a whole bunch of extra work. The only piece of extra work you really need to do is multiply by the derivative of that top term, the x squared, and you get times 2x, and then you just plug in 1. It's 1 times 1 minus 2 times 2, which is negative 1 times 2, which is negative 2. And that's that first question for half of you. Now I'm going to go look at the other first version. So this was quiz A, so quiz B. So if you're like, that example wasn't good enough, here we go. So in this one, we're still splitting this guy up to two integrals. One for the integral from a to b of f of x dx. And one for the integral of from a to b of negative 3 dx. Then again, we know the integral from a to b of f of x dx, which is a plus 2b. And then we have to integrate negative 3 dx, but that's pretty easy. We just get plus the evaluated at a and b of negative 3x. And then you just plug in the bounds, and you get a plus 2b minus 3b plus 3a. You could also subtract and throw a negative sign in between those. I just said that minus a negative was plus. And then you should have gotten 4a minus b. So this answer was actually really nice, unlike the other version's answer, assuming you got to the same point. Then on our other one, they had to the other test had to plug in 5x plus 1. And so you just plug in 5x plus 1 times 5x plus 1 minus 2, and then multiplied by the derivative of 5x plus 1, which is 5. And you could stop here on this version, because that's it. There's no plugging in a number on this one. So because I made the substitution harder, I was a little nicer about this. But people really didn't mess up the actual substituting the 5x plus 1 part. They mostly messed up the either doing the chain rule or like deciding to do tons of extra steps that have no relevance to the problem. A lot of people got faked out by the fact that there's like a derivative sign here, but this is just means the derivative of the integral, since f of x equals the integral of, y times y minus 2 dy. And so there's really no more work here. We're just done once you plug in 5x plus 1 and multiply by the derivative of 5x plus 1. All right, second problem was the same on both versions. So that's going to be easy for me. You had to, okay, so average value, all you do for every average value, and anytime you hear average value, is you just integrate the thing from the bottom bound to the top bound, from 0 to 4. And here we had to distribute a little bit, so we get 2x to the 1/2 plus x to the 3/2 dx. And then we just divide by the width. That's what average value is we do area divided by width. And that's it. So a lot of people were able to integrate this. Some people messed up the distribution, but way fewer than last week, so that was nice. We're evaluating at 0 and 4 of 2x to the 1.5 over 1.5 plus x to the 2.5 over 2.5. And this is still all divided by 4. And then if you plug in 0, all this becomes 0, so all you had to really do was plug in 4. And so the laziest answer was 2 times 4 to the 1.5 over 6, 1.5 times 4, plus 4 to the 2.5 over 10. It's 4 times 2.5. And that was our laziest answer. So remember, it's just area divided by width, and area we figure out by integrating. And that's it. So average value is pretty family friendly once you remember to divide by the width. And a lot of people forgot to divide by the width, or didn't prepare for the quiz or something. I don't know. All right, the bottom ones. I kind of just swapped the U sub in both of them. The problems were very, very similar. So in this version, making the bottom U was correct. U equals 8x minus 2x cubed. We take the derivative of this, and we get 8 minus 6x squared. I still have some people like completely leaving out the dx when they take derivatives, and that's like really sad panda land to leave out the dx, because then they leave the dx in their problem, and then they integrate it, and then they get like an x in their answer that has nothing to do with anything else, and that's a bit of a bummer. So we get du equals 8 minus 6x squared dx, and we feel pretty darn good about this because that's exactly this stuff. And so this integral was just du over u squared. Now, a lot of people integrated this and got like a u cubed over 3 on the bottom or some other stuff like that, and that was a bit of a bummer because all you had to do is rewrite du over u squared as u to the negative 2 du, and then the doors were open to you. You raise the power by 1, divide by the new power. You just get u to the negative 1 over negative 1 plus c, and we plug in what u is, which is 8x minus 2x cubed to the negative 1 over negative 1 plus c. And thank you guys so much for using my chat in here as a robotics meetup chat. I really do appreciate that. It makes it very easy for me to find questions. All right, in the other one on here, you have to make u equal to natural log of x minus sine of x, and I apologize to our 4th period people if anybody's in here, because I did not tell them that the derivative of natural log of x was 1 over x. Some of them figured it out, but I was more forgiving in 4th period in my grading. How do you skip ahead on the live stream? Yeah, I'll fight you. The derivative of natural log of x is 1 over x minus cosine of x. And we have 2 over x minus 2 cosine of x. A ton of people said that this was half of du. It's not. We multiply both sides by 2 to get 2 over x minus 2 cosine of x dx. So yeah, a lot of people messed that up and called it a half. But once you get here, the integral is just u cubed du, and because we had a 2 du times 2. And so it's 2 times u to the 4th over 4 plus c, and it is just 1/2 times that garbage, natural log of x plus sine of x to the 4th over, no, I don't need over 4, plus c. Yeah. All right, to not beat the bush too much, the other version just had a negative 2 on the bottom, and the other version had a 1/4 here. It was extremely similar. I'm not going to go through the whole other version when it's just off by a constant, because I did that on purpose. Thank you, Calculus Sucks. Kennedy does not play Fortnite. No. Kennedy played a lot of Slay the Spire today, though, so I have a lot of push-ups owed. Alright, so now I got a ton of early ask questions on the review, so I'm probably going to head to the review now and just start slamming out the questions. Let's see, where's my first page here? Oh, nothing on the first page was asked. Weird. It's almost like people finished that in class. He only plays manly games like PUBG. Are you kidding? Yeah, I like myself too much to play PUBG. Team Fortress, oh lord. Okay. Yeah, who's the science teacher? One of the biology teachers makes fun of me for the fact that I like turtles, and so yeah, I get hated on a lot for that. All right, so starting in chapter 2, there were a lot of questions. So in this question is a hilariously maybe convoluted way of asking for you to take the derivative of sine squared of x and plug in pi over 4, because it says the rate that these are increasing are the same. So the derivative of sine squared of x is equal to the derivative of kx, and then it says solve for k, but the derivative of the side is k, so all you do is take the derivative of sine squared x, you get 2 sine x cosine x, and you plug in pi over 4, and you get 2 times pi over 2, or root 2 over 2 times root 2 over 2, which conveniently is 2 times 2 over 2 times 2, which is 1. And so that one's just 1. People are asking for questions. Yet, chapter 2, number 5, that's my very next one. So let's reset this and jump in. So implicit, people love implicit. It's everybody's crowd favorite. So we take the derivative of x cubed, we get 3x squared. We take the derivative of 3xy, and we go, oh, that's the product rule. So we get plus 3y for the derivative of the first times the second, plus 3x times dy dx for the first times the derivative of the second. Cool, done with the product rule. Plus 6y squared dy dx, and this equals 0. And now we just need to solve for dy dx. So the preferred method is to move the step without dy dx to the other side. So you get 3x dy dx plus 6y squared dy dx equals 3x squared, or negative 3x squared, whoops, minus 3y by subtracting it over. Sorry, reading the comments, they're super focused. And then we just divide by the stuff that's multiplied by dy dx. And we do that because we can factor out a dy dx and get 3x plus 6y squared in parentheses. And it's just this stuff divided by this stuff. And so you can cancel out all the 3's and you get negative x squared minus y over x plus 2y squared. And this is exactly this guy, just with the negative pulled out. And Eric does not suck. Be nice. Kennedy, do something hard. Yeah, okay. It's not everybody else's fault you got all 5s on the quiz, Andrew. Alright, I'm not going to do 6, even though it was requested, because all you do is find the slope. If you're finding the slope of the line tangent, you're finding the slope. So you just do y2 minus y1 over x2 minus x1. And that's how I got 5/3. Okay. So as far as what was requested next, somebody requested 7. Actually, I got multiple requests for 7. I remember this one. So the first part of 7's easy. Nobody really has a hard time with this. You take the derivative, you find the slope. And huzzah, you plug in -1, you get 7 is our slope. And now that you have 7 as the slope, you know it's A, B, or C. And it's not just a YOLO 1 and 3. Like, there's a way we can figure it out. And the way we figure it out is by plugging -1 into this. We get -4 into the original function, is what I mean by this, to find the y value at -1. Plus 5 plus 3, and that's 4. So we know this goes through -1 comma 4 and has a slope of 7. So all I did was say I move forward 1 in my x, so I move forward 7 in my y, and so this goes through 0, 11, and my y-intercept is 11, which makes C the answer. Okay. Now, let's see. My next questions are chapter 3, 1, 2, 4, 5, and 7. So I know there were some requests in chat for 7. What does the free response question on the final look like? Look at page 3 of your packet. Something like that. All right. So going to this. Oh, do I get to skip to 4? Oh, sick. All right. So I'm skipping to chapter 3, 4. How many inflection points does this guy have? To find... Oh, that's not the right thing. I fail again. To find inflection points, all I do is take two derivatives, 12x to the 5th plus 45x to the 4th plus 40x cubed minus 1. And then I take another derivative, 60x to the 4th plus 180x cubed plus 120x squared. And now you might notice it's like super duper nice. It's not actually horrible. We factor out a 60x squared, and we get x squared plus 3x plus 2. And that's super easy to factor. So we get our 3 critical points. Well, okay, I'll factor it one more step. 60x squared times x plus 1 times x plus 2. So I get to test 0, -1, and -2, and just make sure they change concavity at those points. So, there's totally enough room to do this question in the packet. Don't worry about that. Yes, I'm going to do the free response question, Seth. Give me a second. You're killing me. All right, so -3, -1.5, -0.5, and 1 are what I plugged into this one. And if you plug into the factored step, and this is something that people who have continued to retake this continually do not do, is they do not plug in their points into the factored step of the second derivative, which is so much easier. Because if you plug this in, you realize both of the parentheses are negative if I plug in -3, so negative times negative is positive. And if I plug in -1.5, it makes only one of the parentheses negative, the x plus 1 one, and so that's negative. And so it changes there, that's an inflection point, so that's 1. And then at -0.5, they're both positive. Everything's positive. We're happy. We change again. That's 2 inflection points. And if I plug in 1, everything's still positive. So there's not an inflection point at 0. So there are 2. So 5, I got quite a few questions on online. Oh yeah, that's how I got started on this. The document I put online. A lot of people responded to that. I had 24 messages to that. That's quite a bit. All right, so the second MC mistake in this is to read about the velocity and circle the velocity graph, which is that the velocity decreases, then levels off due to air resistance. And if you think that's what's happening, you're like, oh, it's A, but no, it's not A. It's not A. This is not a velocity graph. This is an acceleration graph we're looking for. And so what the acceleration is doing is decreasing quickly, so lots of acceleration but negative, and then it stops decreasing quickly and goes to not decreasing, which is 0 acceleration. So we want something that starts really negative and goes to 0, and that's this one. So that's what made that one hard, and what makes it kind of counterintuitive for a lot of people. Could you do 6 on this page? Oh, yeah, I can do 6. That's the very next one. And yeah, physics is totally awesome. I was actually looking at what I need to do to get a physics endorsement earlier this weekend. All right, so for 6, it says, what value does this have a point of inflection? This is way easier to write as x to the -2 minus x to the -3. Wait. Her velocity doesn't decrease, her acceleration does. Oh, word. So I pull down the power and drop the power by 1 and pull down the power, whoops, that becomes a plus, and drop the power by 1. And then I do this again, and I get 6x to the -4, pulling down the -3 and killing the negative, and minus 12x to the -5. And then what I did here is some trickery that a lot of people don't do. on these questions, which is pull out the smaller power. Always pull out the smaller power, which is like the most negative power. And so we pull out a 6 and an x to the -5th, and then all of a sudden all that's left is, in this term, an x, because x to the -4 divided by x to the -5 is just x to the 1, because you subtract their powers. And in the second term, we just get -2. And we're like, booyah. There's something happening at 0, and there's something happening at 2. And so we're just kind of testing. First, nothing's happening at 0. There is no points there. So I said no point in my answers. So it's not a point of inflection. It is an inflection value or something. Like, the concavity is changing there, but there's no point. So I test on the side of my actual points. Oh, and the reason why there's no value is because if you look at the original function, we're dividing by 0 there. And that's why I just completely ignored it for this. But if I plug in 2 into the second derivative, which is this guy right here, the values on either side, I get positive when I plug 1 into this, and negative when I plug 1 into the second thing, and so I get negative. And when I plug in 3, they're both positive, and so that is a point of inflection. So at 2, there is a point of inflection. Huzzah! All right, I need to do 7. I know Kapati sauced this page, as he would say, and he congratulated himself, which feels bad. Yeah, AP Physics is probably not even happening in 2 years. I'd have to write the course. Oh, man. All right. Yeah, I'm going to do the FRQs. Chill, chew. So I want to do 7. If you take the derivative of this equation, you get 3x squared plus 2ax plus b. And if you take the second derivative, you get 6x plus 2a. And the nice part about this is they give you the point of inflection, so you just plug in 1 for x, and you get 6 plus 2a equals, you know it has to be 0 because it's a point of inflection. So you just solve for a, and you get -2a equals 6, so a equals -3. And booyah, I got that one. Can you stream Civ afterwards? No, I can't, Joe Bergen. Then I am given the y value, so I should go back to my original function and just put the -3 in there. So I get x cubed minus 3x squared plus bx minus 4. That's my original equation with -3 plugged in. I plug in 1 and -6, and I get 1 minus 3 plus b minus 4 equals -6. So then I just get b minus 6 equals -6. I add 6 to both sides, and I get b equals 0. Which is the right answer. All right, feels good, man. Haven't messed anything up yet. All right, chapter 4. I had all of them requested. I definitely want to go over the first 2, number 4, number 5. Yeah, okay, I got to do some stuff on the... Can I do all of chapter... All right, I'll do all of it. So we go down to chapter 4 here. Hey, this is this unit. Who knew? Okay. So the first one, it's that trick where you're taking the derivative of the integral, so you just plug in x. Done. Okay, cosine of 2 pi x. Done. Did it. So that's why you study the second fundamental theorem of calculus. It's like really, really useful. And stop being obnoxious, Andrew and Seth. I'm gonna get there. Johanna's pretty sure I'm wrong. Yeah, I haven't looked at it yet, so maybe. All right. The second one is literally just you go to notes 25, the average value. Man, a ton of these ended up being average value questions, hilariously. But this is like an exact theorem in our notes for 25, is that the integral divided by the width equals the average value, or the average value times the width equals the integral. And that's it. That's the answer. So that's just a definition one. All right, in 3, we're given a slope, and we're asking for the average rate of change. This is kind of this unit problem in that we integrate both sides, and we get y equals x squared over 2 plus c. And then we're plugging in our bounds like we're doing average value, but yeah, this is kind of like an average value question that's phrased differently. Because we're just doing y2 minus y1 over x2 minus x1 with our y equation now. That's it. We plug in 4, and we get 4 squared over 2. I'm going to ignore the plus c because I'm going to be subtracting it in my integral. Sorry, in my y2 minus y1 part. Minus 1 squared over 2. And all over the x change, which is 4 minus 1. This is literally y2 minus y1 over x2 minus x1. And we get 8 minus half over 3, which is 7.5 over 3, which is 2.5. Booyah. How do you approach questions like Chapter 4, Number 2? Well, you think about which of the possible formulas in our unit may involve a c, a continuous interval, and the integral of the function. There's like 1 or 2 choices to what is possible for number 2. Like, it's either that, or it's like the second fundamental theorem, or yeah, that's about it. There's not a lot else. We don't have a ton of integral rules. Like, people like to make up new integral rules, like sweet quotient things or sweet product things. None of them work. So yeah, we have like 5 rules, and this is one of the 5. So that's how you approach number 2. You like I know people complain about all the words in the notes, but like the words are there so that you can pass questions like this. That's like, Andrew, do you just have to know it? Kinda. Okay, so there's another idea for how to approach number 2. Here's the other approach. You say, which of these things actually equals an area? And you know what doesn't? 2 values subtracted on the interval. The average rate of change does not equal the area. Dividing the function, a value of the function, by the width of the interval does absolutely nothing. Multiplying the derivative of the function by the width, that doesn't find the area. But multiplying a height of the function by the width, that is area. And so that is an alternative way of going through this and just saying, hey, all the ones that are rate of change are bullcrap. All the ones that involve the derivative are like, what? How does that even handle anything or like relate to anything? And just subtracting values, maybe if those were capital F's and C, that would have worked, but yeah, not the way it is. So there is kind of a idiot checking sort of way. Okay, I got no calculator, 16 MC, and the FRQ. Oh, yeah. There are 9 calculator active questions. There are 16 no calculator active. I tend to put problems you don't need to use your calculator for, but that take longer time on the calculator part. There might be like 3 questions that you need a calculator for on this test. All right, number 4. I got a lot of questions like, how do you approach absolute values? In another document, I put another absolute value question. But ultimately, you need to know how the graph looks like to solve absolute value questions. That's just whether you do it as an integral or whether you do it as just adding triangles or geometry shapes together. You need the picture. So when people try to solve these questions without doing a picture, they always get them wrong. You just do. All right, so anyways, if we look at the picture here, x minus 3 looks something like this. Absolute values have a vertex, at the... okay, it's an absolute value function shifted right 3, so I know it goes to 3, 0. To find the vertex of an absolute value, you always look at what makes the inside of the absolute value 0, because where it changes sign is where the absolute value does something interesting. And then we're integrating from 1 to 6, So my first triangle is 2 by 2, and that has an area of 2. And my second triangle is 3 by 3. Notice how the widths add up to 5. You can always check yourself. So that has an area of 1/2 3 times 3, or 4.5. So I'm adding 2 and 4.5 and getting 6.5. And if you're like, no, I hate that, I want to do like calculus things. Well, this is the negative part of the absolute value, the part that's been reflected up to turn it into an absolute value. And so you can call it the integral from 1 to 3 of the negative of that thing, which is negative x plus 3. And you can add to that the integral from 3 to 6 of 3, or x minus 3. And this would also get you 13/2. It just would take more effort. Is absolute value the only thing you need a picture for? No. Definitely not. We get to like volumes of revolution later, and that's like super picture-y. Picture for number 5 makes things easier. Abso-freaking-lutely. Yes, 5 is another one where you need a picture. Yep. So in 5, 3x minus x squared, if you don't know how the picture looks like, factor out an x. And all of a sudden, you know the two zeros are 0 and 3. You also know, because it's a negative x squared, it's an upside down parabola. And so it's like, boom, like that. And now it's saying, which is in the first quadrant, that has some meaning to us, because it's where it's positive between 0 and 3 here. And so this is just asking for the average value of the function between 0 and 3. So I'm going to set up the average value thing, integral divided by width. And yeah, you just solve this. So you get 3x squared over 2 minus x cubed over 3. And we're plugging in 3 and 0 and divided by 3. So what do you get? You get a 3 times 9, which is 27 over 6, minus 3 cubed is 27 over 3 is 9, divided by 3 is 3. So 27/6 minus 3. So 27/6 minus 18/6 is 9/6, so which is 3/2, which is the answer. Wow. Is that what I said online? No, I said it wrong. So yeah, you guys were right. I knew it, says Nick. Yeah. Oh yeah. Attention to detail is not a strength of mine. Did I forget to divide by 3? What a classic mistake. Tons of people did that on the quiz. All right, I want to, in the words of Mark Capati, sauce number 6 here, and then I'm going to go to the free response questions. So I'm just going to write what this integral is. This means the integral sign. This means dx. This means x. And then everything else in the problem tells us the bounds. And we're starting at 3 and going to 7. Because our width of our integral is 4, and our starting value is 3. And so this is literally just the integral from 3 to 7 of x dx. Boom. Nailed it. All right. I'm going to the free response unless somebody was like yelling at me. Nope, we're good. Where? This one. Wait, what the heck? That one. All right. So, going through the free response questions. This is finally, what do you call the problems in Chapter 4, Question 6? It's the limit definition of the integral. You remember the limit definition of the derivative? It's called the limit definition of the integral if you want to practice more of those. See? You can also just write ones and do it that way, because it's once you get a hang of it, I'm not going to put something brutal on there. The one on the review is really similar. And Dan is right. The widths, the 4s are both widths. They are related. You always do width times I for each of your steps over in the parentheses for x. Okay, to start our free response question. Come on. So the first thing says, find the average acceleration of train A over the interval 2 to 8. This is one of those, can you do y2 minus y1 over x2 minus x1 questions? And I say yes. So negative 120 minus 100 over 8 minus 2. I get negative 220 over 6. And now I just got to get my units right. And that is... average acceleration, meters per minute squared. Got it. As I was walking around watching people work on this, a ton of people did not do the units. If you don't do the units, you get wrecked on a lot of these. So make sure you do the units. All right, next one. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some point between 5 and 8? And the answer is... yes, we go from 40 to negative 120 between 5 and 8. And because the thing says it's twice differentiable, it says it's differentiable, but velocity is differentiable, which means the position is twice differentiable. We all good. We have all the derivatives, which means this thing is continuous, which is all you really need to go, oh, this is continuous. So IVT says we have to go through all values between 40 and negative 120. So negative 100 has to happen. That's it. The intermediate value theorem is super handy. It says you have to go through all the values in between. Got it. It's not a dark room. It's a pretty light room. I'm staring at two different, my iPad and my Surface Pro. And yeah, I just ate dinner, so there's like food here. The lights are on. Come on, guys. I don't even have a gaming mouse, do I? It's just like a pro mouse or something, like, you know, because I'm pro. All right, let's go to C and D here. What did I have for dinner? Chicken Caesar salad and some dumplings and something else. I don't remember. All right, so C. It says at time equals 2, train A's position is 300 meters east of origin station, and the train is moving to the east. So we start out positive. East is positive. It's to the right. And if you remember on axes, right is positive, left is negative. We're writing an expression involving an integral that gives the position of train A in meters from the origin station at time equals 12. Okay, because our problem involves velocities and VA of t is like our big variable in this, we're integrating VA of t. Because if we integrate the velocity, we are going to get the position. Now, because this question is just write an integral, we don't need to like solve it or anything. We just plug in VA of t. Now we need to plug in the right bounds, and so it says we start at 2 and we go to 12. And then because we start at 300, we need to add an additional condition. I start at 300 and then I add the change that happens from 2 to 12 in the velocity. And if I integrate that, it gives me the position from change from 2 to 12. And this will give me where my position is now, this integral expression. So yeah, this is like the position at 12. Now, The next part says we do it with trapezoidal sums, so I need to get the table in here somehow. Oh, I have a worksheet here. Nice. All right. Thuggin'. All right, so we start at 300, and we add a whole bunch of trapezoidal sums. So our first sum is from 2 to 5, so that's 3 wide. And the average of 140 is 70. Then I add the next trapezoid, which is 3 wide, from 5 to 8. And the average of 40 and negative 120 is negative 40. And lastly, it's 3 wide. Oh, wait, it's not 3 wide, it's 4 wide. From 8 to 12, it is 4 wide. And we're going from negative 120 to negative 150, and that average is negative 135. And Joe, you can't put the 300 in the integral. If we integrate 300, we're integrating a position and a velocity in the same question, which is ridiculous. That won't give us anything useful. So we're adding the position to the integral of velocity, which gives us position all together. The integral of velocity is position, and 300 is a position. So yes, you can put it to the right of the dt, Tom. All right, so to finish my question here, this is 300 plus 210 minus 120 minus, and this is the big number, 540. And so we end up being to the west of origin station at 12 if our trap sums are correct at all. We're at negative 150 meters, or 150 meters west of origin station, which was the best answer to that question. All right, so the bottom one is our related rates question. Everyone loves related rates, and because of how this document is structured, I do not have a lot of room to write this. So let's see if I can't change that. Can I get a keyboard? Oh, whatever. I'll just power through the pain. All right, so in this question, we have 2 trains. We have our buddy who's starting, 300? Yeah, 300 meters east. So here's origin station. We got train A here. This is 300 meters. And we have this new train called train B, who's up here in the north, and he's 400 meters up, which means, surprise, that hypotenuse, that's 500 meters. Because you're really good at 3, 4, 5 right triangles. Anyways, it also gives us the equation for the velocity of that. So unlike the other one where we just have a table, here we have an equation. So it says at t equals 2, so we plug 2 into our velocity equation, and we get VB equals negative 5 times 4 plus 60 times 2 plus 125. So that train is moving at negative 20 plus 120 is 100, plus 125 is 225. What did I do wrong? Oh, that's just a 25. Oh, rip. All right, my bad. This is negative 20 plus 120, which is 100, plus 25 is 125. And that is the velocity of that guy. Our velocity of our train A is from the table up top, 2, 100 is this velocity. So now I have dB dt, I have dA dt, and I have A and B and C. So I'm just going to set up my, I called it D, I think. Yeah, D is a better variable than calling that C. Okay, so the distance between the trains squared equals a squared plus b squared, and so you get dd dt. Sorry, 2d dd dt for the derivative of d squared equals 2a dA dt plus 2b dB dt. And then we just plug in all the crap we know. We know a ton of stuff. 2 times 500 times the ddt equals 2 times a is 300, dA dt is 100, plus 2 times b is 400, dB dt is 125, And then, yeah, you just multiply all this out. You get 6 with 4 zeros. Here you get 8 times 125 is 1,000. So it's 1,000 with 2 extra zeros. So 100 grand plus 60 grand on this side, and on this side you get 1,000 dd/dt. And so to solve for dd/dt, we just cross off 3 zeros, because that's what dividing by 1,000 does, and we get 160. And so the rate is 160 meters per second. Meters per minute. Whoops. These trains are not moving that quickly. Do we get calculators on the free response? Not on this one. This is definitely a no calculator. Do we need certain wording for the AP test? Yes, you do. You need to describe what is happening, like, fluently. Okay, so no, you don't need to use a specific set of words. Like, you can get points to B without mentioning the intermediate value theorem if you basically describe the intermediate value theorem. So you have some options with how you say this. But you gotta show that you understand what things mean on this in order to get credit. Will the free response question be from chapter 4? Well, so Anna, in relation to that question, if you look at this question we just had, this was unit 3, the related rates. The question above was unit 4. The middle question was unit 2, I think, intermediate value theorem, and the first question was unit 1. Most free response questions are like all of the units. How do you understand the question first? The understanding the question part and like what to do with it comes from just experience. This is one of the hardest things for me to teach, is how to read these questions and get from it. I mean, for C, it's kind of easy. They say write an integral and use a trapezoid sum. But D, they're just mentioning rates, and so you should think related rates. For B, they're B's kind of, you just need to know the intermediate value theorem lets you touch all the points in between. And A, come on, average acceleration, you given velocity, it's just average rate of change. So as far as reading these, it's very different. Maybe if you wrote easier problems. Okay, Patrick and everyone else, these problems on here are written by the AP tests. I just copy-pasted these. The ones on the tests aren't like this, but aren't copy-pasted. But so there's no easy way. The easy way is to be a pro at every one of the quiz sections. If you're that, you're good to go. That's why the free response tend to be like a huge grade booster for people who get pretty good multiple choice scores, and are a huge grade destroyer for people who get less good multiple choice scores. All right, so the second one, we have these two twice differentiable functions, f and g. We get a whole bunch of values in this beautiful table. And we are supposed to find the x-coordinate of each minimum. So if we look, we should look at derivatives to find minimums. So, doink. If we look at the derivatives for f and g, we see that f switches from negative to positive here at 1. So this is a minimum, because decreasing to increasing is a minimum. But if we look at g, it switches from positive to negative. So if they asked for a maximum, we would have said g here. This is a maximum in g. But it didn't ask for that. It just asked for a minimum. So we say f of x has a minimum at 1, 2. Oh, it just said find the x-coordinate. Okay. Giving this is way too much information. We're just going to say x equals 1. And we'd have to give justification. I mean, up in my picture here, this is enough justification, honestly. They're pretty happy about this sort of thing. But if you just say decreasing to increasing, that would be good enough. That's usually what I do. All right, next one. Explain why there must be a value, C, between -1 and 1 where the second derivative equals 0. What I did for this was graph the derivative. So this is like quiz 17. Because if you graph the derivative, here's my graph of the derivative. If I look at my table, it goes through -1, 0, and my picture online really sucked. I'm sorry about that. And 1 is here, 1, 0, and I'm getting these by looking up at my table and saying, I'm graphing the derivative, I'm graphing these 2 points, -1, 0, and 1, 0. And in between, the values are negative, so I know it looks something like this. Because it's twice differentiable, so that's what I said online, is because the derivative graph is differentiable, there needs to be a point at which this continuously turns around. In other words, a point at which the second derivative is 0, the slope of the derivative is 0, a minimum in our derivative graph, which is an inflection point, which is a place where the second derivative is 0. So this was a sketch it and it becomes really obvious sort of problem. So explain why there must be. It's differentiable. And a minimum in derivative graph is an inflection point. And also, you can just talk about the slope of the derivative at that point needs to be 0. And since this is a derivative graph, the slope where the slope is 0 is a point where that's happening. Show us what you would write on the AP test. Man, you saw my answers on there. This is literally it. I would say it's differentiable. So I'd say that this is the derivative graph. And I'd say differentiable, so the minimum in the derivative graph is an inflection point, and so there needs to be a point where this happens. I wrote what I would write. This is totally good enough. If I wrote this, people would be like, oh, he gets it. This man gets it. All right, now to go down to D. Notice how I ruled out C. It's because most of these free response questions are from all sorts of units. Let's see what we've gotten so far. Find the x-coordinate of each relative minimum. That's chapter 3. Next one, chapter 3. And D, chapter 4. That doesn't make sense, Kennedy. What, my explanation doesn't make sense? That's like 17, dude. And yes, it's one free response question. And I gotta be honest, I kind of uncannily did this. I wrote it during break, but the at-bats are extremely similar to these two free response questions. Yes, Sarah, you can interview me tomorrow. Hadn't we already planned that? Like tomorrow after school or whatever? All right. So for D, this is literally just exactly the U substitution. So this is, if you look at our notes for U substitution, this integral is exactly it. And so this is just f of g of x. We're plugging in -2 and 3. And so we're just getting f of g of 3 minus f of g of -2. And I actually showed really good work on this one, because I actually found g of 3 and said I got f of 1 minus g of -2 is -1, so f of -1. And you just get 2 minus 8 equals -6, and booyah. All right, so studying for the Darnell final. No, I'm not going to study for the Darnell final. I was ranting about Ronald Reagan for about 15 minutes earlier today, though. Ronald Reagan is truly an amazing president if you keep your sight in the very present, and less compelling otherwise. All right, this isn't what I wanted. I wanted this. All right, so some people asked for some other questions. What, Jana got ignored? What did Jana say? There's a lot of things in here. The one on the test is kind of like a mixture of both of these. That's my answer to Jana's question. It's going to be like both. If I remember right from looking at it, there's not going to be any parts of the question that are not like either of these. So, man, I'm giving you like two things and saying I'm going to condense it down to one and give you that. So the FRQ is impossible? Oh my lord. Oh my lord. Just figure out how to do the at-bats on the free response on this, and you should be fine for the test, to be totally honest. All right, so a lot of the questions I got ahead of time related to like doing trig with U substitution, and this is one of my favorite questions to do for that. This secant squared x tangent x one, because this one's a very fun U substitution. So you have a choice here on what you do for U. If you make U equal to tangent x, then your derivative of tangent x is secant squared x. And it turns out that's exactly our evidence here. We get du equals secant squared x dx. And this is just the integral of u du from pi over 2 to pi. And we just raise the power by 1 and divide by the new power, u squared over 2. I don't need the plus c because I got bounds. And I plug in what u is its tangent, so I get tangent squared x over 2. And that's what I'm plugging pi over 2 and pi into, and getting the answer. But one of the things that I think is really fun about this, and again, this is in response to a question I got online. Andrew, yeah, your U substitution is totally legit. And that's what I think is really fun about this problem. When I saw this a few years ago, my mind was kind of blown. And then I remembered that trig substitution's a thing, and then it made more sense. So if you make U equal to what Andrew said, which is secant of x, and then the derivative is just secant tangent, which is like really convenient because we have two secants and one tangent, then you just get the exact same U substitution looking thing where you get U du. Which means you integrate to u squared over 2. I forgot my bounds. And you plug in secant, and you get that you're evaluating secant squared x over 2 from pi over 2 to pi. Turns out these give you the same answer, which is really fun and really convoluted that you can use either U substitution, and it works. So some people had some questions about trig substitution, and I wanted to throw this in here. Can you get the mic out of your mouth? It's about 5 inches from my mouth. So, no? Please back up. Turn your volume down, bro. I wanted to do one more based on some stuff I got online and some... oh my gosh, I'm going to the wrong thing again. And some stuff on the quiz. Make it 10 inches. I can't, it doesn't detach, bro. Alright. So in this question, in this sort of situation, you have to make u equal to the bottom. If you make u equal to the top, you're just going to be a sad panda and things aren't going to work out. I talked about this example in the classes, but I didn't really go through it in all of the classes. So I wanted to kind of go through this. When we multiply dx to the other side and multiply the negative, we get that we have a negative du equal to sine x dx. So negative du is what our top is, and this is the integral of negative du over u to the fourth. And a lot of people are still tempted to integrate the top and the bottom and get u over u to the fifth over 5. But remember, you should always rewrite fractions as just power rule things, because that's how we integrate, and then you're good to go. So you raise the power by 1 and divide by the new power. And what we end up getting is we're just plugging u to the negative 3. Oh, u was cosine of x. So cosine of x to the negative 3, and we're plugging in our bounds 0 and pi over 4. What is cosine of pi over 4? Root 2 over 2? So this is 2 over root 2 cubed minus 1 cubed. Oh, sick. That's like something. 2 root 2 minus 1. So that question's kind of fun. Hopefully you're getting a hang of U substitution. If you're not, really practice. Practicing is so helpful. Your stream is eating my frames. Oh, am I losing frames? Feels bad. The last question I got is about something that the live chat here was complaining about, which is that absolute value questions are hard. Isn't root 2 over 2? No, because it's, yeah, it's negative power. So if I'm looking at, if I'm looking at an absolute value function of sine of 2x from 0 to pi, I really need to know what this graph looks like. So if you multiply by 2 inside the parentheses, that's a horizontal shrink, if you remember from your Algebra 2 or pre-calc days. And so essentially this is just one cycle. What do they call it? Periods? A period of a trig function here from 0 to pi of sine of 2 pi. Or sine of 2x. And so because I'm doing absolute value, I'm reflecting this negative part of the sign up here. So my absolute value function is actually these two pieces. Now, there's a lazy way to do this, and there's like a not lazy way to do this. The really lazy way to do this that I love is to say, hey, this thing, this up hump, is going to have the same area as this up hump, the first one. So since these things have the same area, I do 2 times the integral from 0 to pi over 2 of just sine of 2x dx. That's the lazy way. Like the really lazy way. If you're not happy with the lazy way, you can always just kill the 2 in front and just add the integral from pi over 2 to pi of now the negative sign, because that's what will make it positive, negative sign of 2x dx. And this will work also. So this is how you handle absolute value functions, is you just desperately need to know what the picture looks like to know which part is reflected up. So you can set up the integrals. What if you're not lazy? I just did it. Is it lagging? So this is the non-lazy way. Here you still have to do a U substitution of sorts, because you need to deal with the 2x. But if you remember the shortcut, we can just say this is negative cosine of 2x over 2. When the derivative of the inside is a constant, we can just do the shortcut where we divide by the constant, that constant. And the negative sign of 2x gives us the positive cosine of 2x over 2. And so, blame leg. All right, word. And then you just plug in pi over 2 and 0. You get negative cosine of pi, which is positive 1 over 2, minus negative 1 over 2, so plus a half. And you figure out that each of these things has an area of 1. If you plug it in here, you'll get an area 1, 2. And so these have an area of 2, which always tripped me out when I was learning calculus, that the area underneath trig functions was like whole numbery things, as long as you kept the intervals nice. All right, so Andrew has a question. What if you have sine of x squared? You know what you do? You go to Calc BC and you learn how to solve sine of x squared, because you just give up. This sucks. Now, if you have an x here, all of a sudden you can do this one. You make u equal to x squared. You say du equals 2x dx. I only have 1x dx, and you can do this. But we can't do it without the derivative on the outside. And so we actually just kind of give up. Oh, hi, Brendan. Coasting and boasting. Oh, wow. What a winner. Oh, so, big stretch on here. Folks, are there any other questions? It seems like the chat has devolved to nothing, and scrubs who used to be in my class coming and visiting. Is there anything else I should address before I leave? This is your last chance to speak now or forever hold your peace. Do some limit definition limits at points. Okay. Challenging optimization questions. Yeah, I don't want to get crapped on this. Challenging optimization. I could do one of the ones off the review. So I can do, the retake quiz last week. I'll do that optimization question. What's the derivative of 2x? Okay, limit at a point. So, okay, let's look at those two questions. So let's just go to my sketch pad here. Let's dump all this garbage and go here. All right. So what Andrew's asking about is this thing. Whoops. Yeah, limit as x approaches 4 of like, what's a way to make this question that's actually fun? I got to put an x minus 4 on the bottom, and I do like sine of x minus sine of 4. Yeah, this question looks great. This is totally a question I could put on the test. So I could just ask you to tell me this limit, and this is like, if this is factorable, you know more trig substitution math than I do, because I don't know how to do this otherwise. But the trick here is to recognize that this is the limit as x approaches c of f of x minus f of c over x minus c, which is exactly the limit definition of the derivative at a point, which means this says take the derivative of this thing and plug in 4, and that's the answer. Done. Usually the answers to these come really, really fast once you realize what's going on. The other kind is the limit as delta x approaches 0 of that sort of nonsense. So, what can I do? How do I usually do this on tests? I do it like this. So 4 plus delta x to the 5th minus, what is 4 to the 5th? 16, 256, 1024. Over delta x. And I ask you like what this is equal to. And this is just the limit definition with, instead of x, I plugged in 4. And so all I do is just take the derivative of something to the 5th and plug in 4. 256. And that's it. So these are the two kinds of limit questions that are very likely to be on this test. So that was a pretty good question to ask about the two different kinds. Remember, this is quiz section like 7, and this is 5, I think. Oh, I wrote that where you can't see. This is 7, this is 5. And yeah, good question. All right, the last thing I was going to do is go to my review, or my retake document, which I don't have open. Crap. Now I'm just going to show people how to search my documents. Feels bad, man. This one is what I want. Oh, I got a question. Wait, why plug in 4? Okay. Do I still have that open? Yeah, it's here. So why plug in 4 in both of these? In the first one, the reason I plugged in 4 was because that's what my limit's approaching, and this is the limit definition at a point. And so 4 is like really obviously the dude that I'm handling here. C is here, here, and here in the equation. All of the arrows going up there. So that one's easy. In the other one, the reason I plug in 4 is because the normal limit definition of a derivative is limit as delta x approaches 0 of f of x plus delta x, and I'm doing this on the wrong side. This is actually this stuff. Minus f of x over delta x. This is the equation and what it should look like. And so that's how I created that equation up there. I created something where I plugged in 4 for x in this equation, and all of a sudden, this is that for a function that is x to the 5th. This thing up top here, this is the limit definition with x replaced with 4 and f of replaced with something to the 5th power. And that's how I knew to plug in 4 in that. Hopefully that answered your question. Do a complicated one, dude, with the square roots on the bottom. Nah. I don't even know what that means. So, looking at our retake, and yeah, I make these documents every week. There's a lot of crap in them. Here's our optimization question this week. We had, well, the second half of the week. A baseball team plays in a stadium that holds roughly 55 grand spectators. With ticket prices at $10, the average attendance was 27 grand. Market survey showed that for each drop in 10 cents, the attendance will increase by 300. How should the ticket prices be set to maximize revenue? So this is my way of creating one of those orchard problems without an orchard problem. I really just did a lot of searching on the internet. So the big idea here is that we can't go bigger than 55,000. So if we create anything that goes bigger than that, we're screwed. But otherwise, that 55,000 has no relevance. So what we're using is the actual average attendance. And we're making a revenue equation. So our revenue equation is going to be number of spectators times the price per spectator. Because if you look at this, the S's will cancel, and I'll just get money. And that's what you want for revenue. So my equation for spectators is I have 27 grand to begin with. And for every drop of 10 cents, the attendance will go up by 300, so I add 300 for every change. And then my money for each is I have ticket prices at $10. It drops by 10 cents. That's not 10. For each increase or decrease in price. So we're getting more people every time we decrease the price. And this is our equation. We just multiply this garbage out. And we get 27 with 4 zeros plus 3 zeros x. We lose a 0 off of the 27,000. So we get 2,700x. And minus 30x squared. There's our beautiful revenue equation. This is just 300x minus 30x squared. I'm ignoring the 27,000 or 270,000 because I'm about to take the derivative of this, and I don't give a crap about constants. So then I get dr dx equals 300 minus 60x, and all you had to do is go be like 60x equals 300. Set this equal to 0. And you get x equals 5, so you should do 5 of these jumps. The question asks what should the ticket prices be set at, and the answer is you should subtract 10 cents 5 times. So 10 minus 10 cents times 5 times, and you get 10 minus 0.5 equals 950, and that's the price. So that was the optimization question this week. The only people asking me questions are like Weibel and Chin. Oh lord, what has happened with these live streams? This is the absolute worst. So, on that note, since the questions have fallen apart, except for Andrew Chu, who said yo, I'm going to call it a night. It's 8:16. I want to watch some Expanse and yeah, relax for a moment. Maybe put in your quiz grades. Maybe not. Maybe I'll just do that tomorrow. I put in retakes. Do an optimization with the triangles. Nah, I'm good. I'm going to bed. Well, I'm going to relax and then go to bed. Have a good night, y'all. See some of you on whatever. When's the test? Tuesday and Thursday. And Andrew, if you have other questions, just come in and holler at me Monday after school. I'd be happy to help you after Sarah's interview or whatever. No, I'm not going to help you with your linear algebra. I haven't taken that in a while. Oh yeah, Stream Offline's here.